Next up is Myriam, and she's from Montreal, and she's going to be talking to us about the first high contrast images of near high mass X-ray binaries. So whenever you're ready there, Myriam.
Hi, thanks for giving me this opportunity. I'm Myriam Prasow-Émond. I'm a new master's student at the University of Montreal. And today I'm really thrilled to present you the first high contrast images of near high mass X-ray binaries. So recently there was a press release about exoplanet around a white dwarf. So today it is in the same vibe. So first, an X-ray binary is a system composed of a compact object, so black hole, neutron star, or white dwarf, accreting material from a star. And some recent studies indicate that substellar companions, such as exoplanet or brown dwarf, can exist in a variety of environments, that we have like really close orbit or really wide orbit. And in a recent paper, so Imara and Di Stefano 2018, it was recently argued that X-ray binaries could host planetary systems. However, those systems are more likely to harbor wide orbit planets since there is a multiplicity in those systems. So planet-star or planet-planet interaction are more common. So it will just push the planet over. So the main point is that X-ray binaries are unique laboratories for studying astronomical objects and phenomena under extreme conditions. So about observation, in 2017, we obtained data for 7 X-ray binaries, including 2 sources that we also observed in July 2020. So as I just said, we obtained 3 nights of observation on Keck 2 from 10 to 12 July with the vortex chronograph. And we observed 8 high mass X-ray binaries for about 2 hours each in L band. And we also observed RxJ 1744 in K band. So in this work, we chose high mass X-ray binaries. High mass X-ray binaries is where the star is an OB star. We also chose a near X-ray binary, so about 2-3 kiloparsec. We choose this because we want to increase the chance of detecting substellar companions. So in those systems, planets are more younger, so they're more bright and more hot. And what is really exciting with this project is that we obtained the first high contrast images of X-ray binaries. So I'm really thrilled to present you my preliminary result. So there's a lot of work to do, but we still have really nice results. So first we have EGR G18483 with a lot of candidate planets, as you can see, with 3 here that we don't see well. We also have SAX G1818 with 1 candidate planet and 1H2202 with 1 candidate planets. We also have RxJ 2030 with 2 candidate planets, and the really interesting object, RxJ 1744, that has, as you can see, about 7-8 candidates, but when we do SNR maps, we found about 20 candidate planets. So I encourage you to go see the poster of Louis-Simon Cuité. He describes the subject in more details. We also have Gamma Cas, which is a pretty controversial object since we're not sure it's an X-ray binary. But what is interesting is that we have 2 planets here, so Gamma Cas A and Gamma Cas B, that were already detected in the past. And it's a really close object to us. And finally, we have 4U1700 with 3 candidate planets and 4U2206 with no candidate planets. So this leads me to this question, how can we determine if those candidates are planets, so substellar companions, or just background source? So the first thing that we can do is called the proper motion analysis. So basically we just take more data in a few years and just see if the planets moved or not. For the present data, we can do this with Gamma Cas since we had data from 2017, but for the other object, we will have to wait a few years. For RxJ 1744, we can construct a color magnitude diagram since we have L band and K band data to see if the candidates are more likely to be stars or planets. Also, what we will do, we will fit the flux coordinates of the candidate with the Nelder-Mead optimization code with the VIP open source code to have a rigorous estimation. Finally, we can run the tridigal galactic model of stellar population. So basically, we'll just estimate the number of stars in a certain area to estimate the probability of having background source instead of companions. We might also do a follow-up data with OSIRIS to measure the spectrum of the candidates. So the main conclusion is that substellar companions can exist in extreme environment. This is why this work is so important and so exciting. Also, this study leads to novel science because exoplanet orbiting about white dwarf, neutron star, and black holes is really a new subject and really is interesting. About future work, we will conduct a statistical study for the presence of substellar companions in every type of near X-ray binaries. So we will include here low mass X-ray binaries. So we already have data, but we will probably ask for more time in a few weeks. Yes, so I really talk fast since I'm really stressed, but thank you a lot. Here is my contact info, and I'm really happy to take questions.
Thank you, Myriam. This first question comes from Aniket Sahai, which is, which image reduction algorithms were used to obtain the images?
So we use the ADI. So we have a data queue, and we use ADI to have the, if you see those images, they're all ADI processed images. You want me to explain more ADI, it's fine.
No, I think we can, if there's details about ATI, we can throw that up onto the Slack channels. The next question is, if these are stellar companions, do they form before or after the supernova that created that black hole?
If they are substellar companions, they would be formed after the supernova. That's what we think. That's why they are so far. So that's why, as you can see, the orbits are really big. So no, they're more likely to be formed after a supernova.
And this one comes from Josh. Given your current data set, what can you say about the statistics of the presence of companions in these types of systems?
To be honest, I'm really new to this subject and I just started my master's, so I can't really answer this, but there will be a paper in about 1 year about this. I'm sorry to not answer this.
A question from me is, you mentioned that you're thinking about a statistical study. So what's the sample size that you're anticipating?
We will have about maybe 15 to 20 X-ray binaries. But it's a new subject, so it will just be like the first paper on this subject. And of course, we hope that more paper will follow this.
And then one more question from me is, when you look at that image with 20 possible candidates, what's the non-detection that you expect for that? Or do you expect all 20 to be real exoplanets? There are really a lot of star in those system, but and the really wide orbit are most likely to be background source. But as you can see here, the B is really close to the X-ray binary. So this one is, we hope so, a planet. And like all the one that we can like really see are probably, we hope that they will be planet, but as you can see, G and H are probably not planets. All right, well, if there are any additional questions, we'll put those into the Slack line. Thank you very much, Myriam. Appreciate the talk. It was a great talk.